All right, so in this video lesson, we are going to learn how to calculate, how to evaluate those double integrals over general regions. Okay, so at this point, before we get started, I gotta make it clear. At this point, all of our skills we've learned, the methods we've learned, are all enough. But the idea now is that the problems we have done prior to this point are all, and when I say the problems, I mean the double integral problems we've been doing prior to this point, or up to this point, are all limited to rectangular regions. So we have seen in our earlier learning that we can calculate a double integral over a rectangular region like this, where we put them into sub-partitions of the region, and then we take the integrals and all that, and we accumulate over a rectangular region. So that's strictly the kind of problem we've been focusing to. And then the skill we've learned is we apply only on problems limited to rectangular region. And so now general regions here means we're studying those double integral problems where the region we're looking at is no longer rectangular. So a region is like this, we can have a region like that, a general region, or a region like this, just basically anything no longer a rectangular region. So you can look at simply a triangle, right? It's a region like that. We consider all of these as generally as the general regions. So that's why in my way of understanding, I'm using the term general regions here in my title of the discussion topic here, simply just to make it align, to align that with many textbooks authors who name these the region that way. But in the way how I see it, general regions simply means a non-rectangular region. So now we're learning how to handle those integral problems where our regions are no longer rectangular. So here I would say non-rectangular region. That's really what to understand right there. All right, so it could be a circle, it could be a loop around, and it could be a triangle, it could be just parallelogram, it can be a trapezoid as a picture of the region, it could be anything non-rectangular. All right, and so that's the idea. So now to get started, I am going to bring in one problem. So now, with this problem I bring in here as an example. And let's call that example 1 in this lecture over here. Okay, we would like to evaluate the double integral over a given region, where our function here is x squared y dA. Okay, and so where the region is as following. So at this point right here, it's going to be almost it's going to be a lot better to just describe the region by drawing a picture instead of giving it in worded description. So most of the time here, almost the whole time here, I'm going to just describe the region by drawing the shape right here on the board. So the region we have is as following. So I have one parabola shape going up that way, so one parabolic shape right there. And I have another parabola going this way, okay? And the two parabolas here intersect at that point 1, 1. All right, and it goes 0, 0. And so the parabola in our understanding up to this point. Okay. So that's the regions right here. See, so this region here is clearly non-rectangular. That's the x-axis. That's the y-axis. And so let's just assume that for anyone learning in this lesson up to this point of your learning in your majority in learning, then a parabola is just on the most standard either a square function like that one could likely, and I purposely, unlike many textbooks authors who present this, I purposely hide away the equation of these parabolas, but it kind of gives you a hint that up in our learning at this point, And I said it in words earlier. These are the two parabolas. One of them is a sideways parabola, and the other one is an upward parabola. Okay, so in your learning up to this point, in your learning experience up to this point, because this video lesson is meant for anyone who's ready to do the double integral, so your algebra is of course assumed to be the fluent. And so parabola, any parabola at our understanding point here is either a square function, a standard square function, and the most standard one is the x square function, and then the other one, when it's sideways like this, usually it's a square root function. Okay, and on standard, just the basic square root, y equals square root of x. So, and the point is, again, I don't want to write down the equation here, but I'm kind of giving a clue like that somehow. So the best clue I have here is it's the two parabolas here goes through the 0, 0 and 1, 1, and it has a trap. So the region being trapped between the two parabolas here is the region that we're taking this double integral over. All right, so this is exactly what it means by taking a double integral over a general region right here. This is the general region. This is R. All right, so let's have a better picture of this on my computer station. All right, so this is the picture over here. The region is here, and the point is right here at 1, 1. Okay, and we got another point at 0, 0. And so I will tell the equation of the shape later. Okay, I will point down the equation of shape, but right now all I'm giving a clue is that when the parabola is pointing up this way, it could be some squaring, some quadratic function, and when the parabola is pointing sideways like this, it's a lot of times in our algebra understanding it can be some square root function. Okay? And we'll get to all that, but the shaded general region is here, being shaded in red color right here. All right, and so now before we can advance further, allow me to introduce an extension. I see this as an extension of the Fubini's theorem. So we have learned Fubini's theorem earlier, but that was when we were handling those problems on rectangular region. So now we're looking at the extension. So it's a theorem, but I see this as a Fubini's theorem for non-rectangular regions. It's an extension of the earlier Fubini's theorem that we've learned. So let's consider a double integral problem. So just as usual, it's a double integral for a function of two variables. Okay. But R here over a region R, but R here is a non-rectangular region. So the word is highlighted here, is non-rectangular region. But here's the thing, when we're handling a problem like this double integral problem, and now further, if the region R here can be described as the set of all x and y, the set of all x comma y such that the x value is being trapped between two constant value a and b, and the y value is being trapped between two functions in terms of x. So these two inequalities are important right here. So now let me swing back on the board, and this is time that I'm starting to explain about the nature of the picture of the region that we've seen. So this is the region, and I said it's the region that's trapped between some two parabola curves right here. Okay, and so what does that mean by the fancy writing that if the region here, the same region can be expressed as the x comma y such all pairs x comma y, because any point in here is a point x comma y. Okay, any point in there is a point x comma y, any point in that region. But now what does that mean by x is between the some value a and b, and then y is going somewhere from some function g1 of x less than or equal g1 of x less than or equal y, and then y is less than or equal to some other function g2 of x. What does that mean by these two inequalities right here? Okay, so let me bring in the actual picture to make it more clear. Right. So now think in terms of this picture right here. Now, at any point x comma y, think about the tip of my mouse cursor right here. So I can see that the y value, no matter where you at, for any x value, so horizontally doesn't matter where you at inside of this region, but the y value, the highest it can get is the upper boundary of this curve, of this region. And the upper boundary is a curve. Okay? And so in the same way of looking at it, the same region, if you're at any x value that we freeze right there. So think about we freeze the x value, and then at some x value right here, as I said earlier, the y value only goes as high as hitting the curve, and the y value only goes as low as hitting the bottom curve, the lower curve. And so now that means we express the upper curve and the bottom curve here as some two functions of x variables. And so that's what it means by as long as we can recognize the y value. So think about we freeze the x value. Okay, so on my picture right here, pick a point x comma y, but we freeze an x value. We freeze an x value. That's why I'm drawing this vertical stripe right here. Okay, and so on this vertical stripe, we're at some x value, but the y value goes only in between, only being restricted, limited between the upper curve and some lower curve. And so now that means we're going to have to see this upper curve here in the picture as some g2 of x. And this lower curve here is some g1 of x. And that's the idea right there. And that's what this inequality here means. And then once we recognize that nature about, and so in the way how I was doing that, in order to recognize this, a lot of textbook authors deliver the method that you draw a, see I fix the x value, so we draw a vertical line, and that vertical line is restricted, got heights being restricted between the upper curve and the lower curve. Okay, and now with those vertical stripes here, so now think about it, where do we put those vertical stripes? So now putting those vertical stripes, the starting point we can put is at this point right here, and the ending point is about right here. That's the last vertical stripe we can put, because see the vertical stripe keep getting smaller and smaller, because the height at any x value will always be restricted between the two curves here. But then the last, think about it, the really last, the vertical stripe we put is right there where it hits to that ending point of the curve, of the region. All right, so in that way, so now when we're in this situation, and that's what it means by, see, x is in between some two constant values right here. So now right here, when we apply that understanding right into this problem, here's what I'm seeing it. I see the curve, I see the region R here is being described as all x and y, x comma y points, that's x values is anywhere between 0 and 1. See, because vertical stripes, I can only put those vertical stripes that's starting at 0 for x and ending at x equals 1 right here. X equals 1 right here. Okay, so that last vertical stripe is here, and then the beginning one is at x equals 0, and that's why I have this inequality. It's constant values trapping the two constant values that trapping the x variable in between, and then I see the y variable is being anywhere above. See, so this curve now, it's a curve, it's just a curve, and that's the reason why right in the beginning when I first introduced this, I kind of going a little abstract here in terms of, because I didn't want to show the equation. So this curve here, now we can express that as a function in terms of x. And so now it must be the x squared function that falls below this, any one of our vertical stripes here. The lower end of each vertical stripe is restricted by the x squared function. Okay, and now I'm really telling you that this curve is intended as the x squared curve. And then the upper curve here, at least in this region, the upper curve here is a sideways parabola. And I mentioned that term earlier. This is now the square root of x function. All right. So indeed, these are given information from the beginning, but I just want you to understand it. So the point now is that as long as any point, right, your region can be described as the set of all points, so that the y value at for any x right here, the y value is being restricted between some two functions of x. and then the x here changes from some two, changes value between some two constant value. Okay, this is a description of our region. So now, that's what it is to understand about the region right here. So I have seen that in this picture right here, I can see the region here as that description. Let's get back to the theorem. So now further on the theorem right here, as long as we can describe, so that's why it's a case here of when we're handling this double integral problem over a non-rectangular region. So when we're in that case where we can recognize, where we can describe our region R, okay, as the y value is being trapped between some upper curve and some lower curve, and the x value runs or changes anywhere from between an a value, a constant a value to a constant b value, then this is how we can do our double integral problem. So Fubini's theorem that we've learned previously allowed we to do all this, but now the inner integral here first have to start out in terms of x first, and then we let x change from the lower function to the upper function. The inner function has to be integrated in terms of y first, and then as we're integrating that, we gotta integrate from the lower g1 of x to the upper g2 of x, and then the outer integral will be done in terms of x. Okay, and that's the order here. So now we apply the Fubini's theorem, but there's a certain order depending on how we recognize our integral here. So you can see that y changes from the low function of x to a high function of x. So we gotta integrate. We gotta find the integral in respect to y first, going from a varying the function g of x to an upper g of x right there. And then the next one in the order right here is we're gonna integrate everything in terms of x, for x running from value from a to b. So now in that case we're ready, particularly for our function here. The g1 is x squared, g2 is square root of x, and then the x value is running from 0 to 1. So now setting it up, this is how I'm setting it up. The double integral over the region that we have seen in the picture, the function here is x squared y dA. This can be calculated as, the first thing I'm going to set up, the iterated integral from x squared to square root of x. This is g1 of x to g2 of x. The function here is x squared y, and then I have to integrate it in respect to y first. And then I'm integrating it again, whatever outcome coming out from this, I'm going to integrate it again from 0 to 1 in respect to x. That's how we set up our integral, our double integral into a set of iterated integrals right here. And then this is sort of like, it's a driven outcome right here. The inequality that we recognize here driven us into this particular iterated integral, because we remember when we learned about iterated integrals, there are two different ways how we can set up our iterated integrals. But so now in this case right here, we are driven into this specific case where we're integrating in terms of y first, and then after that we're integrating in terms of x. Take a moment, right, to really understand the idea. So the connection here is that we are integrating in terms of y first because y is being changed between a variable function to another variable function, whereas the x will change from a constant to another constant. And so the varying part right here, we're integrating it first. Okay, and then the other one going from a constant to a constant, we're integrating it after. All right. So that's enough with the idea, but now after you have successfully set up your iterated integral, the rest of the problem is going to come out easy. All right. And so now, just like how we've been doing with Fubini's theorem, 0 to 1, but we have to handle this integral first. So think of that here as, so what I'm having here is going to be x squared, 1/2 x squared y squared, and we're going to evaluate all of these from x squared to square root of x. And then whatever that outcome will be, we're going to integrate again in respect to x from 0 to 1. But that's for later. So for now, let's go ahead and finish out evaluating this antiderivative here from x squared to square root of x here. All right, so in my next step, it's still an integral. But substituting these two expressions in here, I'm looking at, so square root of x substituted into y. Here, substituted for y in our expression. It gives me a 1/2 x squared times x. And then minus, now 1/2 times x squared, but now x squared substituted in here, we're ending up with an x to the 4th. And then we're integrating that. See, so now at this point, everything is in terms of x. And that's making it completely possible to move on, integrating it in respect to x further as the next step. All right, but by the way, it really bothers me writing my expression like this. 1/2 times x squared times x, and minus the 1/2 times x squared times x to the 4th. So I'm going to rewrite this in a cleaner version. 1/2 x cubed minus 1/2 x to the 6th power. All right, and now we're integrating this particular problem right here in terms of x, and then evaluating that from 0 to 1. And so now that gives me, in the next step right here, I'm looking at now a 1/8 okay, x to the 4th minus 1/14 x to the 7th. And now we can evaluate this from 0 to 1. And now at this point it should be easy for anyone, so I don't need to explain too much in details for any one of these steps right here. So the answer comes out being, so it's 1/8 times 1 to the 4th minus 1/14 times 1 to the 7th right here. So the final answer comes out being 6 out of 56. And we can reduce that into a 3 out of 28. That is our final answer for this double integral. All right, so example 1 is technically done, but let's not be finished with that. I brought up this example 1 right here in the intention to understand that it's actually one problem right here to understand and to explore. So let's roll back to that point where we understood, we try to give the description of this region right here. The region is just a region being trapped between some two parabolas. One parabola is pointing this way, the other parabola pointing this way, right? And so now, see, the region, that's the region, all right? So here, I'm talking about in a different way of seeing it. The same region is just the same region, and it's still the same problem. I purposely want to give a completely different solution right here so that we have in-depth study and in-depth understanding of the situation right here. So the same general region right here. This is the picture. That point right here intersecting between the two curves is 1, 1 and 0, 0 down here. Okay, so now think about it this way. Think about for any x, y points right here. X, y points, right? Being inside of the region somewhere. Now if I draw think about if I freeze a y value. So I draw that big fat, so let me redraw my shape here a little bit. So my shading is making it a little too busy for the picture right here, but all right. So that's the shading. But now think about, I pick a point, x, y. There's a point right there. But now I'm going to draw a horizontal stripe. A horizontal stripe is to indicate that what I have here is a fixed at some particular y value, And I can recognize that, hey, wait a minute. My x value in this case, because at this particular y value, my x, that's why I'm putting a horizontal stripe this time. So on my horizontal stripe this time, then left and right is being limited, being restricted by the two left and right curve, the left side curve and the right side curve. left side curve and right side curve. So in our understanding, left side curve, we can express this curve right here. Well, in the earlier solution, same problem. In the earlier solution, we saw this curve here as y equals square root of x. But now same curve right here. I'm seeing that as a left side curve that limits each of our horizontal stripes. And so now in that way, I'm seeing that we can re-express this curve here as y squared equals x. This same exact curve right here, I can re-express that algebraically as y squared equals x. Now this other curve here in the earlier solution of the same problem, I saw that as y equals x squared. But now I'm seeing this as a curve that's to the right, that limits on the right end of each one of our horizontal stripes right here. Then I'm going to see this. I'm going to re-express this curve as square root of y equals x. Now, someone may question me that, hey, when you take the square root of x, the square root both sides out of this, don't you get x equals plus and minus square root of y? I agree, but the point now is that, see, technically it was, but the reason I got straight into the positive one because we're on this first quadrant. All right, and then allow me to save that explanation at the minimal right there. But so now that's how I express this curve right here in terms of y. See, so now the way how I'm seeing it, when we freeze a y value, that's why we produce this stripe horizontally. X changes anywhere from the left curve being y squared and ending at the other curve being square root of y. So now in this way of how I'm seeing it, the same region, but now I can describe that a little bit differently. It's contain all of the x comma y points where the x value, or how about let's say, yeah, the x value is anywhere between left curve is the y square function, and then the right curve is the square root of y. So x here is expressed as an inequality being as the value trapped between some two functions of y. And then the x, and the y variable is indeed, so these are the horizontal stripes this time. So horizontal stripes, think about it, these horizontal stripes, the first one from the bottom up, the first one here starts at y equals 0 way down here. And then we keep putting more stripes up, and the last one we can do is y equals 1. And I understand that my picture is getting pretty busy here. So I can see that y variable changes from 0 to 1 for this region. All right, so now the region is exactly the same, but it's a completely different description. And so now that same theorem again. Suppose we're going to handle this exact same double integral problem. And it's a non-rectangular region. But now in a different case, the same r, but if we can describe r as, see, x changes from some lower function of y to some upper function of y, and then the y value changes from some lower y value to some higher y value. Then if that's so, we can proceed on calculating this double integral by first integrating in respect to x. So again, similar to the earlier case. So this was the highlight of the description of our regions. Okay? But the similar rule over here, the generality here is that for the variable that's being changed, that's changed from a function to another function, some general expression to another general expression, then we have to integrate in respect to that first, according to Fubini's theorem. And then once we've done with that, we're going to integrate again in respect to the other variable that remains from some constant to another constant. And so that's how we handle it in this case here. If we recognize our general region as this set of inequalities. For the exact same problem, I'm going to set it up as following. First, I'm going to integrate in respect to x. So our function here is x squared y. I'm going to integrate in respect to x this time. But then remember, we broke it down earlier. X changes from some general curve in terms of y and ending at some other right-hand side curve in terms of y again. So now this is the the bottom end of our integral, and this is the upper end of the iterated integral. So now it runs from y squared to square root of y. And then as an iterated integral, I'm going to integrate from 0 to 1. But the next variable to integrate in order, dy. That's how we're breaking it down. So it's the same problem. And I'm expecting the same result at the end, but it should come out. But the way we're handling it, the way we produce a problem was done differently. And so here in the next step, yes, the integral from 0 to 1 in terms of y remains the same. But now let's handle this integral here. So Fubini's theorem say now we can just go ahead and take the integral as usual. So now in respect to x, I'm looking at a 1/3 x cubed y. And then I'm going to evaluate all of these from the y squared to square root of y. Y squared to square root of y. So that means we have an integral from 0 to 1. And here I have a 1/3 times y to the 3/2 power times y minus 1/3 times y to the 6 times y. And integrating that in respect to y. All right. And then so the cleaner version of this y 1/3 times y to the 5/2 minus 1/3 times y to the 7. All right. And so now we're going to integrate in respect to y. So the first term here gives me, so it's 1/3 times 2/7 times y to the 7/2 minus, and now 1/3 times 1/8 times y to the 8. And we're evaluating this from 0 to 1. And so I'm running out of space here, so allow me to start going skippy with these calculations here. And so all in the end, it's going to come out 2/21 minus 1/24. And it will all come down to 3 out of 28. All right. So that's how we're evaluating this integral. Same exact result right here, but two different ways of how we're setting it up. All right. And so before we head into a further extension of this kind of problem right here, or further details of how we handle it, we at this point have learned enough ideas of that. But I just want to clarify that once, for anyone viewing from this lesson right here, if you read side by side with the textbook, any textbook that you are using in your math course right here, then many professors, many authors who write calculus textbooks tend to describe. So let's say again, same region, and right here from our example, same region. So the same region, but if you can describe that as region R over here, and if you can describe that according to that theorem I brought up earlier, if you can describe the region here as x variable changes between a constant value to another constant value, and the y variable is changing from some g1 of x to g2 of x. So if you can, the same exact region, but if you can describe that in this way right here, then many textbooks author refer to this as a type 1 description right here. A type 1 description. It's just to get things systematized like that. But I tend to break away from these names because over my years of teaching, I feel that it's more heavy for students to worry about memorizing which case is type 1 and which case is type 2. So I take it out, and I just want to make you feel flexible. But I just want to push you to reach the next flexibility. So any region can be described as one case, type 1. So type 1 or not, it's your choice to understand the name of the type. But the idea is expressing it. Think of each vertical stripe. So each stripe right here got height, y value between a low curve and a high curve. That's what type 1 is. And then the x is going from some starting value to an ending value being constant. That's type 1. But like I said, being whatever type, don't try to memorize that. Okay? So same region. If you can express that, because earlier I was showing that in the example. See, now we're putting the horizontal stripes in here. And then if we can successfully do that, meaning we can express the x variable as a variable that changes from some low function, h1 of y, to some other high function, h2 of y. And then the y variable in this case right here is changing between some two constants, c to d right here. Yes, many textbook authors refer to this case here as a description of type 2. So in a way how I worded the theorem, it's the same theorem, but in a way how I worded it, if you can express the exact same region, if you can express that under description type 1, then you go with that integral. And if you can express that, so it's all about if, whichever that, I want you to understand these are just different tools, different options. So whichever one here that works better for you, you go with that. Okay, so if you can express your whatever region you have as a type 2 description right here, then you use that other integrals that was shown earlier in the earlier part of our discussion here. Okay, and so this example, at the end of this example, we already got an answer to that. Before I completely move out from this example over here, then you can see that this is one region where we can express that in both types. And that's why I didn't even want any of my students, any of my viewers to worry about, is this a type 1 or type 2? Because ideally in my years of doing this, the first thing is to see if I can describe the same region here under both types. That's how I'm seeing it. I recommend being flexible in both ways. And then later on, we're going to learn some examples where the way it is, some regions, the way how it's given, it's only better to be one of the two types, meaning it's going to be easier to work as a type 1 description or easier to work as a type 2 description. So again, this region right here can be easily described in two different types, as two different types, two different forms. But some other regions later on we work with, one form is going to give some better advantage and some other form will be some disadvantage somehow. All right. And so now, let's look at our next problem here, and let me label that example 2. We want to evaluate another double integral over a general region, non-rectangular region. Our function here is x plus y squared, and we want to integrate that in respect to dA. And the region we have this time, and again, it's impossible for me to write it all in a narrow space of the board right here with all the worded description. So let's just take a look at the picture, and the picture will tell the story. So how about, it's a region like this. One curve is a parabolic shape again. And this is one. And this other curve here, all right. All right, so here we go. So that's the general region. So this time you can see that the general region here got, as far as vertical stripe right here, it has a clear start and a clear hard stop right here. A clear start and a clear stop. Meaning we got a clear vertical line at start and a clear vertical the line at the ending at the stop right here. And so the curve here, the upper curve here is about some y equals x cubed plus 1. And the bottom curve here is some, and it's not really that parabolic, but close enough, x cubed. And so now in a way how we see this picture right here, clearly, the R here, the region R clearly is, and is at its most direct right here. We can see that the x variable runs, because now think about if you put any vertical stripe, x variable is corresponding to a vertical stripe. So as a x value right here, a vertical stripe, and the vertical stripe at any x value is limited between, there's an upper curve which is already given clearly, and a lower curve which is also already expressed. And then those stripes has, as I said earlier, those stripes right here together, right? This region has a clear starting stripe and a clear ending stripe right here at x equals 0 for this line. And this one right here is x equals 1. And so in that way right here, clearly I can see that I have the x variable changes between some two constants, 0 to 1. And the y value here changes from, see, x cubed is the bottom, and then x cubed plus 1 being the upper one. X cubed and the x cubed plus 1. And so now with something like this, yes, if you want to see that as a type 1 description or whatsoever, yes, you can go with that. And then you have a robotic way of, hey, so if it's type 1, and we'll go into that way right there. Okay, but I want you to have a clear understanding. It's not just about the type 1 or type 2. So here you go. You're not working as a computer. When it's this case, we do that. When it's this case, we do the other way. Okay, but so now when the picture is like that, and you have expressed the region, then the integral is going to be expressed. You see, the y variable is the one that's being restricted between some two varying expressions. So we are integrating the function in respect to y first. So the function here is x plus y squared. But we're integrating that from the low being x cubed, and the high is x cubed plus 1. And then we're integrating it again in respect to x from 0 to 1. And so now, once we have successfully set it up, our iterated integral, now we can go ahead and proceed further. The inner one here needs to be taken care of first, and now we treat that as just any ordinary integral that we've done from calculus 2. So here I'm looking at xy plus 1/3 y cubed. And then I'm going to be evaluating this expression here from x cubed to x cubed plus 1. And then I will, whatever it will come out, I'm going to integrate that in respect to x. And so what I have now in the next step, from 0 to 1, we got x times x cubed plus 1 plus 1/3 times x cubed plus 1 cubed, and we're subtracting x to the 4th minus 1/3 x to the 9th power. And we will be integrating all of this in respect to x from 0 to 1. And so, taking your steps to get this done, we're going to end up with so our answer will come out 103/84. All right, and so that is the answer. And so now, as far as getting the answer, we're done. But now let me go back to the other board. And I want to explain that. So in this problem right here, what if right from the beginning I didn't click? What if in the beginning that we didn't find out that it was a type 1? So clearly this was a type 1 description. But what if we wanted to do this region here as a type 2 description? Meaning, think about we put a horizontal stripes. Okay, you are not forbidden from doing that. You are not forbidden from doing that. There's no one saying that it's illegal doing that. But what matters here is the reason I brought up this problem is some regions one description is going to be a lot more advantageous than the other one. So obviously right now, describing this region as a type 1 description works a lot faster. We got the answer done. It didn't take too long. Okay, so what if? Okay, so think about what if I want to use horizontal stripes, and as I said, we can do that too. But now there's something. If you're going that way, in this picture right here, there are a couple of things you got to watch out for. We got to watch out for the part where it's breaking up the picture. The part where it's breaking up the picture. So yes, if you put the horizontal stripe right here, there's a one breaking up line right here, and then there's another breaking up line. So there's that separate region where those horizontal stripes between, they stay 0, 1 and 0, 1. So, and then in between here, there's another area. See that from that line and up, anywhere you put a horizontal stripe, it's this curve is the left and this line x equals 1 is the right. And then when you're down here, putting any horizontal stripe here, you got this x equals 0 is the left and this is on the right. And then yes, your y value, your y variable can go from 0 all the way up to whatever it hits up here, okay, which is whatever value that is. But the point now is that we have to, if we're going with horizontal stripes right here, we have to break it up into a lot of area and regions. That's the reason why I avoided that right from the beginning. So type 2 will work if you're patient enough to pull it through, but you're going to have to run into 3 separate. So in this region, again, there's 2 different ways of seeing left curve and right curve. And then in this region down here, left curve is a vertical line and right curve is a curve. And then on this way right here, the left curve is a curve, but the right curve is a straight vertical line right there. So it's too much broken up parts or pieces of the graph right here of the region. And that's why, if you're going with type 2 description right here, it's going to be less advantage. Okay, and it's going to give you a lot of the headache to keep track of all the regions, and we have to add up all the regions together for the double integral. And that's the reason why I didn't go with that. So this example was meant, right, for you to realize that some region, it's by the way how it's set up right there, it's better, right? It's more natural to come up with a type 1 description. All right. And now let's come up with another example where I call that example 3. And again, let's evaluate. This time our double integral is on a function x squared minus y squared, and we want to integrate over the region R, where I'm going to draw the description again of the region. It's a triangle as following. This is 1, 0. I mean 0, 1. Now negative 1, 0, and this is 1, 0. So the region is right in here. That's the region that we're integrating. So pretend or think about or imagine that our function here is some curve above this, right? And we're integrating, we're accumulating volume. That's a way to understand that. Over this region right here. It's a general non-rectangular region. Okay, so would a problem like this allow me to present my own experience, and I'm going to come back and explain why we shouldn't go the other way. I mean, like I said, it's not illegal to go the other way, but it's going to take the longer and a lot less effective. So here I'm going to go with the horizontal stripes here. Think about, I'm going to fix a y value at a particular y value right here. Okay, and I'm going to produce for myself a horizontal stripe. So this horizontal stripe right here is clearly, think about no matter where you're tracing up and down your horizontal stripes right here, then it's always going to be between the 2 edges here. So there's the right edge and there's the left edge. All right, and then and obviously the stripes, the horizontal stripes can be placed. The lowest one here is y equals 0, and the highest one up here is y equals 1. And so what are the 2 edges here? And see, here it's just a nice description of a triangle. So, and you can see that right from the beginning, it didn't even come with equations or anything like that. And so now it's our responsibility to find out what are the expressions in terms of x, in terms of y, for these two, the right edge and left edge right here. All right, so now I'm seeing this left curve right here. Yes, as a function in terms of y, it's going to be x equals minus y plus 1. This right curve right here is x equals y minus 1. All right, and so now this is the left curve, this is the right curve. And so this is how I see the region R as far as the description. The region R is a set of all x comma y such that at anywhere you place your horizontal stripes, the x value changes anywhere from y minus 1 to minus y plus 1. That's how I see the change in the x values, because anywhere I put the horizontal stripes here, there's a left end and there's a right end that restrict our line. So that's x between these two. And then the y, and then the x value is going to be in between 0 and the y value is going to be anywhere between 0 and 1. And that's how I see this description of the region. Okay, so it's got so the left and right is being limited by left curve and right curve, and then the up and down is going from a constant to a higher constant right here. And so now, once I saw that, yes, if you really love the name, it was called a type 2 description right here in this picture. But now as far as setting it up, the double integral over the region R for the function x squared minus y squared, I can calculate that as, for the inner one, the first one to handle. You see the horizontal stripes going up and down, but x is going from left to right. X is being limited between two variables curves, so I have to integrate in respect to x first. Okay, and then so the function here is x squared minus y squared, and then we're going from the bottom curve here, the left curve is y minus 1 to minus y plus 1. That's how I'm seeing it. And now as an iterated integral, I'm going to integrate again in respect to y from 0 to 1. And that's how I'm setting it up there. All right, so now the way to go is clear from here. We're looking at, I'm going to integrate this inside the integral over here. And so that will produce for me 1/3 x cubed minus xy squared, and I'll be evaluating this expression from y minus 1 to minus y plus 1, and then all of that outcome I'm going to integrate later on in respect to y. And so now in the next step, it's an integral 0 to 1. I'm looking at a 1/3 times minus y plus 1 cubed minus y plus 1 times y squared, and then minus, now I'm going to substitute that in there, giving it 1/3 times y minus 1 all cubed, and minus again, and then here y minus 1 times y squared. All of this here will be integrated in respect to y. Okay, and then anyone viewing the lesson here is fluent enough with this easy work right here. I'm going to leave the steps for you, for viewers, for students who learn with me to pull that through. All right, and just now when I was going over on my computer, I noticed I had a typo here. So it was supposed to be adding here. And so in that way, our final answer came out being 0. All right, and so as far as having an answer to this integral problem, to this calculation of the double integral problem over a general region. It's done. We're done. And it wasn't that challenging at all to get it done. But then, right here from the beginning, right? The region is the region. What if we wanted to describe this as a type 1 region, a type 1 description? So to do that, to think of this as type 1 region, then think about we place a vertical stripe this time. So meaning at any instance for x value, at any x values, yes, you can see that you can place horizontal stripes starting from x equals -1 and ending at x equals 1. That's easy. Okay, so x comma y such that x is going anywhere from -1 to 1. That's easy. Okay, but what about the y value, the height of our vertical stripes? What's the limitation? But now when you're placing in those vertical stripes right here, you're gonna start noticing there's gonna be a breaking up point right here, a point where it's breaking into two separate behaviors. On the left-hand side of this line right here, on the left-hand side, any vertical stripes is restricted between this curve going up and 0. And then when you go past this line right here, then the behavior changes. We got y limited between this falling down line right here and that. So it's another breaking up nature to the point that it's making things complicated, and I don't even want to get in there. And that's why going with type 2 that we've done previously was a lot more direct than going with type 1. But I'm not saying that we cannot go with type 1 description. It's still completely okay to get it done, but it's going to take a lot more effort. Okay, so really type 1 or type 2 description is all just different options right here. There's always in my years of working with this, the rule of thumb here is there's going to be one that's going to be less work, less effort for you. Go with the one that has that costs you less effort. Okay.